Hello everyone, my friends, my viewers at home. My name is Adrenaline, the Bazuka Prophet, and today we're going to be talking about a very interesting video that talks about molecular orbital diagram and how you feed electrons into molecular orbitals and also the bond orders. But please, if you have not yet watched my previous video under molecular orbital and its theory, please do well to first of all help yourself by going to my YouTube channel and watch that particular video before you watch this particular one, because it is a continuation of the previous video. Now, today we are going to talk about what is molecular orbital diagram, and we'll be using examples to illustrate it in such a way that even while you are on your own, you can be your own teacher because of the understanding you will derive from this video. Hello? So let's move ahead. Now, what is molecular orbital diagram? Now, molecular orbital diagram shows the relative energy and the number of electrons in each molecular orbitals, as well as their atomic orbitals from which they are formed. That's what we call the molecular orbital diagram. And and the way it is being drawn is very, very simple. Is the rule guiding it relates to the way to the filling of electrons into atomic orbitals, and the rules which include the Abau's principle, the Ohm's rule, and the Pauli's explosion word principle, which we are going to be making use of here in this particular video. And the question here that we're giving was to draw the molecular orbital diagram and indicate also the bond orders of the following molecules of ions, as you can see right here on the board. So you will have to follow me as I take it slowly for you so you can be able to understand. But have it in mind, first of all, that chemistry is not difficult. In fact, you'll be so glad that you are right here watching this video to pump all the errors. Now we move straight away. Now follow me as we move. Now swiftly we take solution one. Take on solution one. So let's continue. Now what do we do here? So we said that for H2, remember for hydrogen molecule, it is formed from here two hydrogen atom. Meanwhile, there are two types of molecules. We have what we call the homonuclear and the hetero. For homonuclear, it involves same atom, while hetero, it involves different atom. You get me now? And in the case of homonuclear, the electronegativity difference between the two of them is equal to 0. Why? It is same atom, as you can see for hydrogen. Now the diagram is as follows. I come here, draw. Here is the energy. Now it's just like addition, whereby this is for hydrogen here. This dash is also for hydrogen here. Now, in the middle, in this case, is where we have the anti-bonding, and here for the bonding molecular orbital. Why this one you are seeing here? Remember I told you earlier that this one that you are seeing here are the atomic orbital, which is hydrogen and hydrogen here. So, and remember that the configuration of hydrogen here, which is just 1x1, this is for hydrogen, atomic orbital for hydrogen. Here, 1x1, another atomic orbital for hydrogen. But here, we'll be taking what we call the sigma. Remember, it's x and x orbital interaction, which is sigma bonding only. So here become sigma 1x, and here is also what we call anti-sigma 1x. Now, I draw the diagram. It's not up to scale, just for you to understand it. Now, look at me. When these two they interact, Remember, I have told you that the bonding molecular orbital is first filled. You dey first fill this down first before you dey go to this one. So when these two dey interact, what happen now? I'm having two electrons, meaning one electron from here will combine with another one electron from here, which is from here. So here it comes, let me give you of the red pen so that you can easily follow. So this is what you have. You get me now? So that this is what we now call the H2. And from here, one calculate for the bond order. Now bond order is equal to the number of electrons in the bonding. Is how many now? Is it not 1, 2? Remember, the must be of opposite spin according to Pauli's structure principle. So here become 2 minus. Is there any electron in the antibonding? No. So here become 0 over 2. So that altogether 2 minus 0 is 0 is 2. So 2 divided by 2 is what now? 1. So the bonding order for hydrogen molecule is 1. And because it is 1, it is stable. And because why is it stable? Remember I told you earlier that whenever the number of electrons in the bonding is more than that of the anti-bonding, then it is stable. As you can see here, there is no electron in the anti-bonding, but there is in the what now? In the bonding. So and on that note, and from this bond order 2, one can know the bond, how many bonds that exists between hydrogen molecule, which is just something of this nature. I hope it is clear. Straight away to example 2 for dihydrogen ion, which is 2. Move straight away. The same pattern I followed. Remember that for H2 plus, it is formed from two species. See hydrogen atom 1, which is for the atomic orbital, plus hydrogen ion. But when these two come together, this is what is formed now. I think I'm having like Li2 plus. So it will be Li for the first one plus Li plus. It's as easy as that. So that is the rule and pattern for it. So I come here, the energy or potential energy. Now, atomic orbital. Another atomic orbital. For this one, remember, for hydrogen atom here, it is just 1x1. But for hydrogen ion, remember that for hydrogen ion, no electron is found. So it means here become 1x. But let me explain for those of us who are slow learners. So here is 1 plus. So is it not 1x0, which we don't know, right? It's not just 1x, but no electron is found in it. So this is hydrogen ion. Remember the antibonding sigma 1x, which is antibonding. Here too, the bonding 1x. Don't draw it, not drawing it to scale. Now what do we do here? Remember, when these two interact, I'm going to be having something of this nature. Get it must fill here first. When there is filled up, we move to the other one. So that is how it is. So from here now, the bond order is now equal to the number of bonding now. The number of bonding now is 1 minus, is there any? No, 0 over what now? 2, which will give me 0.5. Now what does this 0.5 indicate? This 0 here, first of all, indicate to us that this molecule does not have any bond between them. But because there is now a decimal point which is 0.5, so that the kind of bond that should be found there should be weak. And most times it is ascribed to molecules, to species that are having charges most of the time. So this is what you are saying. So we'll move straight away to the next example. So move to the next example. So we'll move here with example 3. Now what do we do next? So we come here. Here is the energy. This is for what now? Helium. helium plus 2. Now remember, for dihelium ion, remember it will be formed from helium atom and helium ion, from what we said, and they both have atomic number of 4. And when you draw the configuration for helium, okay, we'll do it together. For helium, we're having something like this. 4 is 1s2, 2s2. While for the helium ion, then 1s2, 2x1. How are we having 2x1? Remember that one electron has been lost. So I'm having 1s2, 2x1. So what do? Meaning we have two diagrams here. Now the first diagram here, which is for the 1x, is that this and this will interact. This and this will interact. So we come here, draw it here. Okay. So come here now. 1s2. Here is 1x2. Then come here again. That's for helium. That's for helium ion. Here is also what now? 1x2. So this is for the antibonding, sigma 1x. And here is anti-sigma. Here is sigma, which is the bonding now, for 1x. So what do? In this case here, remember, when these two interact, what will happen? You first of all feel here, feel here. You get me now? Why for the, if you remember, it means that I'm having these 2 plus these 2, will it not be 4? So if it is 4, and that this 1s can only accommodate maximum of 2 electrons, so it means that the remaining 2 electrons will then move to the what now? To the anti-bonding, which here will also be 1, 2. We are done with the 1x and move to the 2x. And the 2x is the same idea too that will also follow, which is here and here. You get? So put here that sigma 2x, and here 2 is also, permit me, let me rub this off. There is sigma anti-sigma 2x. So remember, so if here is 2x2, here is what now? 2x1. So feel like this, and here. When these two interact, remember the bonding is fit first, then it comes like this. And one is not remaining here, it's now fit the other one here. So which you draw something like this. I hope it's clear. Now, from here now, remember that this part here, they are the atomic orbitals. They will then come forth here to know for the bond order. The bond order here is equal to, now, how many electrons are in the bonding? Look at it. The bonding here, is here not the bonding? Is here not for the bonding? So count 1, 2, 3, 4. That's for the bonding. So here is what? 4 minus what of the antibonding is 1, 2, 3. So here is what now? 3 over what now? 2. Here will give me 1 over 2, which is equal to 0.5. So it shows that there's a weak bond too. There's also what found here. So one can bring them out that the molecular orbital diagram is simple. Come here, just bring all of them, and here is sigma 1x 2 anti-sigma 1x. Then sigma 2 x 2, the anti-sigma 2x1. So this is what you are seeing here. They will then move straight down to the last one, which is for lithium. And in the case of lithium, it's number 4. lithium 2. The same idea that lithium 2 is formed as a result of lithium plus lithium. There is no anion here. And for lithium, the first lithium atom which is A, let's say S1S2, 2x1, but it has the atomic number of 3. The other one 2 is also lithium 3, and 1x2, 2x1. Then the energy here, then we drop this one x2 here, we interact with this one x2 here. 2x will also interact with 2x what now? 2x1 here. So I come here, we draw for the first one. Here is 1x2. Here is 1x2. Sigma 1x. Here is sigma 1x. Here is anti-bonding. Anti-bonding. Now we move straight away. Of course, when these two interact, this is for lithium, this is for lithium, this is for lithium molecule. Now when these two they interact, of course, we're having 4 here. So you just have to feed 2 here first, or move the many 2 that's remaining, feed the anti-bonding. Then we'll move straight away to the other one, which is 2x again. Here is like this. There is 2x1, there is 2x1. So something of this nature. Remember, I'm not going to scale, just do the sketch work here. So what do we do? Now when these two interact, remember here become sigma 2x. Here is sigma anti-sigma 2x. So when these two interact, only here will be feed, because there is no other one here that will come to the antibonding. And from here, the bond order here is now equal to how many electrons are found in the bonding? 1, 2, 3, 4. Now 4 minus. Is there anyone found in the antibonding? Yes, I mean just 2. Over what now? 2. So the answer is now 4 minus 2 is 2. 2 divided by 2 is what now? 1. So this element or this machine is stable. And the kind of bond that should be found there is just 1 bond. Now we are done with that of the molecular orbital diagram of homonuclear for the first case. Move to the second case in our next video. God bless you.